Good morning, class, and welcome to this lesson on Kinematics 7, free fall vectors and terminal velocity. This is going to be like free fall part 2, okay? We will be able to draw vectors for objects in free fall and explain terminal velocity. So we're going to get a little better conceptual understanding of free fall and then talk about this concept of terminal velocity and what that means, okay? So um, let's take an object. We'll take an object that is being dropped off a building, okay? And at this point, it is released. It is released, okay? So at this release point, the velocity is equal to 0. So if I was going to draw, I'm going to draw velocity vectors as red, you know, I'm going to draw velocity vectors as red and acceleration as green. At this point right here, this object has no velocity. It has no velocity, velocity is 0, so there's no vector, it's just a dot, okay? It's nothing. However, remember that acceleration is constant. Acceleration is constant. So if we were going to draw an acceleration vector at this point, it would be a constant vector. It's going to be accelerating down at 9.8 meters per second squared, okay? Or free fall. So after 1 second, after we'll say 1 second, the ball is going to be right here. We'll say that's t equal to 1. Okay, t equal to 1. We will have a velocity vector. This velocity vector is going to be pointing down because it now has a velocity, and that velocity is going to be 9.8 meters per second because it accelerated 9.8 meters per second squared. Okay, so in 1 second it gained 9.8 meters per second, and then the acceleration is going to be constant, and so the acceleration at this point right here, is going to be 9.8 meters per second squared. So let's go to t equals to 2 now. Okay, t equals to 2. After 2 seconds, it is going to gain even more speed. It's going to gain even more speed, and this is going to be a bigger velocity vector, and this is going to be 19.6 meters per second because it gained another 9.8 onto this one. Okay, so it's 19.6 meters per second, and the acceleration is still going to be 9.8 meters per second squared. Okay, 9.8 meters per second squared. So it's still going to be the same thing. So we'll do one more situation right here. We're going to do it down here. And the velocity is going to be even bigger. I ran out of space down here, but essentially it's going to be, what is that going to add up to? 29.4 meters per second, and the acceleration is still constant. So what I am trying to tell you is that acceleration is a constant value. If we drew vectors for this thing being dropped at any single point, the acceleration is going to be the same thing every single time, and the velocity is what's changing. Also, one side note, notice the distance in between these is all increasing. Because if we look at our equation, x equals 1/2 gt squared, notice that the time is squared. So x is going to increase exponentially. It's going to increase exponentially because t is being squared. This is an exponent. This is an exponent. So it's going to increase more and more and more every single time. Okay. Now I'm going to give you another situation, just to kind of contrast this a little bit and hopefully make it a little bit clear. Let's take an object that's being thrown pretty much straight up in the air, okay? So it's being thrown straight up in the air, and I'll keep the same colors here. And so it's going to be thrown up in the air with a speed of 30 meters per second, okay? So as it gets thrown up, after 1 second, oh, excuse me, I didn't do acceleration, I'm sorry. So the acceleration right here is going to be the same. It's accelerating at 9.8 meters per second squared. And for the sake of being easy, I'm going to call this 10 on this one, okay? So 10 meters per second squared, because acceleration is still down, acceleration is still down and it is still constant. So after 1 second, it's going to be right here. What's the velocity going to be? Well, if the velocity was going up right here and acceleration is pointing down, that means the velocity is going to change by 10 meters per second in the opposite direction. So this right here is going to be 20 meters per second. And notice the acceleration is still 10 meters per second squared. Okay? After one more second, the velocity is going to be 10 meters per second, and the acceleration is still 10 meters per second squared. And then at the top of the curve here, the velocity is going to be equal to 0, and the acceleration is still going to be 10 meters per second squared. And just for the sake of being easy, I'm just going to mirror this and do it all at once. So notice here, after one more second, the velocity is now going to be 10 meters per second, 20 meters per second, and then 30 meters per second. And at every single point, 10 meters per second squared, 10 meters per second squared, 10 meters per second squared. So at every single point along this curve, notice the acceleration has never changed. This is a very confusing thing to most students because we think, oh, this thing is going up, therefore the acceleration must be pointing up. But the acceleration, notice it's changing by 10 meters per second every single second, right? And notice it's changing in the down direction, or the negative y direction, so to speak. So the acceleration is the same at every single point. It doesn't matter if it's going up or if it's going down. The acceleration is constant throughout. It is the velocity that changes, and so we have to make sure that we understand very clearly what acceleration is and what velocity is. Velocity is a vector indicating the speed, direction and speed of an object. Acceleration is the change in velocity. So, moving on, we have this thing called terminal velocity. Okay? Terminal velocity basically includes air resistance, okay? It includes air resistance, okay? So if we say take a skydiver, jumping out of a plane, and this person, there's a door right here, and this person jumps out of a plane. When this person jumps out of the plane, we're going to say their initial velocity is equal to, their initial velocity is equal to 0, and their acceleration is equal to 9, or we'll say 10 meters per second squared. So they jump out of a plane, they have an acceleration of 10 meters per second squared, but this includes air resistance. So because this includes air resistance, this is not free fall. Remember, free fall is an idealized motion in which there's no air resistance. So this person's going to gain speed, right? So I'm going to draw this person falling through the air. And these are all different points of time here. Okay, so this person is going to gain speed. So we'll say after a second they're going 10 meters per second. And I'm just going to make up numbers here. I have no idea what these numbers should be. I'm just going to make stuff up right now, okay? So this person's going 10 meters per second, and then this person is going to start going, we'll say 18 meters per second, then 25 meters per second, and then we'll say 31 meters per second. Okay, I'm just making this stuff up, all right? Notice, this person is still accelerating. Their velocity did increase, but is it increasing at a constant rate? So notice, from here to here, it was 10 meters per second squared. From here to here, the acceleration is more like 8 meters per second squared. From here to here, 7 meters per second squared. From here to here, 6 meters per second squared. Like I said, I'm just making these numbers up. I'm not sure if that's actually how it happens or not. And at some point as we go, I'm just going to make this person's path go this way, okay? At some point along this path, this person's going to reach a speed, we'll say 50 meters per second, and their acceleration is going to be 0 meters per second squared. Meaning, because of air resistance, and I'm going to talk more about this with forces, this person has gravity pulling them down, gravity is pulling them down, air resistance is pushing them up. Because of air resistance, this person falling is no longer going to accelerate. This person is going to reach a certain speed, and then the speed is going to be constant. This speed is going to be constant. So the acceleration slowly decreases until it finally reaches a value where there's no more acceleration. This person cannot go any faster whatsoever, okay? So this person cannot accelerate because air resistance is pulling them back. Now, this is in free fall. This wouldn't happen. This person would just go faster and faster and faster. But in real life, with air resistance, things do reach a terminal velocity. They can no longer go any faster due to air resistance. So notice how the vectors here change in this reality, in this real life situation versus something like this where it's constant the whole way through. Okay, so based on this video, you should have a better understanding of how to draw vectors and have a better understanding of what acceleration is and velocity is for objects in free fall.